Hey guys, welcome. My name is Dr. Stewart, and today we're going to learn about the immune system. So I feel like if we're going to talk about viruses and bacteria in this class and how different types of microorganisms can affect us or affect humans, make us sick, it's important for us to kind of get a quick overview or maybe a little review of how the immune system works. So obviously the immune system is our body's way of defending ourselves from things that have entered into our body and want to make our body their home. Things like bacteria, parasites, viruses, even protists, right? So our bodies are basically like big nutritious bags of salty fluid and it's warm. And so we're the perfect environment for microorganisms to live, but we need to keep those guys out. And that's the job of the immune system. So the immune system comes in really two different forms here. So the first form of the immune system is called innate immunity. So INNATE, and that's immunity. So innate immunity refers to the parts of the immune system that are always present and they're always doing a pretty good job. Like these can be, your skin is an example of the innate immune system because it always does a good job of keeping things out of the body tissues. Another example of the innate immune system are cells like macrophages and neutrophils, because these cells always do a really good job of attacking and consuming cells that have entered our body that shouldn't be there. Natural killer cells are another example of the innate immune system. Those cells are really good at identifying and killing bacterial cells, but also like cells in our body that have turned cancerous. So the innate immune system is always there. It always does a pretty good job. It does a good job like when you're 2 years old, and it does the same good job when you're 20 versus 40 years old. It doesn't really get worse or better at defending the body from different illnesses. That is in direct contrast to what we're really going to focus on today, and that's called the adaptive immune system, or adaptive immunity. Now, adaptive immunity is the part of the immune system that can actually get better at fighting intruders through time, whether those intruders are bacteria or viruses. So it can kind of learn to fight and defend the body better with experience. And this is so important for our survival and our health. And the two cells that or the types of cells that make up the adaptive immune system are lymphocytes. And lymphocytes come in two different types. You have T cells and B cells. You guys have probably heard T cells and B cells. And these guys look pretty small. So if you were to look at what a lymphocyte looks like, they look like these little spherical cells with really large circular nuclei inside the cell. In contrast, like a red blood cell would be a little larger than a lymphocyte, and it would be like, I don't know, maybe about this big. So that would be like the size of a red blood cell. Oh, we should shade them in red just to kind of show what's going on. So that's like a red blood cell right there. You guys get the idea. All right, so this is a lymphocyte. These T cells and B cells, they look like that, and this is a red blood cell. Now, in order to kind of understand how these T cells work, we should first focus, or how these lymphocytes work, let's first focus on T cells. So T cells, they go through when you're very young in life, right? And when you're like a toddler, right? Like newborn to a toddler. These T cells are going through a training process. So and this training process happens inside your thymus, so which is a organ right here that lies here in the cervical region. So on your thymus, all of these immature T cells are going through a training process, and really that's just the body's way of making sure that we can trust these T cells so that they don't attack our own healthy body tissues. Now we've got a couple 100,000 different kind of versions of T cells, and each version of a T cell is going to be sensitive to one particular antigen. Now, a little bit of terminology here. An antigen is just a term for anything that elicits an immune response in the body. So it could be a bacterium, it could be a virus, it could be like even our own tissue that might confuse the immune system to respond. That would be an example of an autoimmune condition. So we have all these different T cells, hundreds of thousands of different types, different versions, and they're all sensitive to a specific and unique antigen. We first make sure that we can trust these T cells in the thymus so that they don't attack our own tissues. And after we can trust them, these T cells are going to leave the thymus and they're going to travel all throughout the body to places like the lymph nodes. They're going to travel throughout our bloodstream, and they're going to spend their entire life looking for the particular antigen that they are a match for. Many times, these T cells will never find their match. They're just going to float through our body tissues, constantly looking, and they'll never find it, and that's okay. That goes into saying that these T cells are actually very long-lived. Now, if this T cell, it actually finds its particular antigen that it is sensitive to, then it's going to become active, right? Now, before we kind of talk about this activation process, we need to talk about the different types of T cells that exist. So when we're talking about T cells, all right, I'm going to kind of talk about them right here. So these T cells, we'll talk about B cells later, they're going to exist in two different forms. You're going to have CD4 T cells, and you're going to have CD8 T cells. Another name for CD4s are helper T cells, and another name for CD8s are cytotoxic T cells. They both look like this, spherical cells with a spherical nuclei. Now, helper T cells, when they become active, they have the job of releasing all of these stimulating chemicals or signals called cytokines, which are going to stimulate other parts of the immune system to become active. They're going to produce and release cytokines or these signals. They're going to activate CD8 T cells. So these guys, when they're activated, they're going to release cytokines, and these cytokines are going to activate the CD8 or the cytotoxic T cells. With a name like cytotoxic, all this means is that these T cells, the CD8 T cells, those guys are going to kill other cells that are a problem, right? So they're very powerful, very kind of dangerous cells that are able to kill cells that have entered our body very effectively. Okay. Now, in order for these CD4 T cells to become active, they need to bind onto the antigen that's their specific match, right? Now, what'll happen is that basically we'll have another immune cell in the body, like a macrophage or a dendritic cell that's kind of cruising around the body, constantly looking for things that don't belong. It might find a viral particle, like a virion of, I don't know, some virus. It's going to engulf that virus, and it's going to take it to a lymph node, because that's where these CD4 T cells are hanging out, these helper T cells. And it's going to start presenting them to different CD4 T cells that are in this lymph node. A lot of them aren't going to match that particular virus because they're only a match for one virus. But if it does find the one CD4 T cell that matches that virus, that CD4 T cell is going to become active. When it becomes active, it starts dividing like crazy. So it goes from one of these cells to hundreds, thousands, hundreds of thousands of these CD4 T cells. And these CD4 T cells, they start releasing cytokines. That's going to activate all of the CD8 T cells, and those CD8 T cells, they're going to start killing those viral particles. Okay, so that's a really important thing. Now, after that virus is completely knocked out, some of those CD4 and CD8 T cells are going to turn into memory T cells. That's the last part of T cell. And these memory T cells are going to hang around for years and years, just floating around the body, constantly looking for that same virus in case it ever shows up again. If it does show up again, then it's going to rapidly change into CD4s and CD8. it's going to convert back into these CD4 and CD8 T cells, and they're going to start doing their job right away, but it's going to happen much quicker, so they can knock out any secondary infection much more rapidly than the initial infection. After infection is kind of resolved, though, it's worth mentioning that these CD4s, there's hundreds of thousands of these guys now, there's hundreds of thousands of these guys, they're all going to die, and the only thing left over are these memory T cells. So that's kind of the gist of how T cells work. Now let's talk about B cells, because those guys are probably even more important to our immune system. So B cells, just like T cells, are floating around. They're only sensitive to one particular antigen. We've got hundreds of thousands of different B cells, and they're all inactive. They're just kind of cruising around the body looking for their specific antigen. Now, when a B cell binds onto that specific antigen, let's say it's the same virus that the T cell reacted to, that's going to start the activation process of this B cell. But in order for the B cell to fully activate, it needs to do two things. So activation of the B cell, activation of this B cell depends on two things. It needs to bind onto antigen, and it needs to receive cytokines from, who released those cytokines? Well, this guy over here, the CD4 T cell. So, in other words, what I'm trying to say here is that the CD4 helper T cells, they don't just activate the CD8 cytotoxic T cells. These cytokines also are going to activate the B cell. Okay? So after activation occurs, after this B cell receives the cytokines and it binds onto that viral particle, it's going to do one thing right away. It's going to start dividing like crazy, right? It's just going to start dividing. That takes a couple of days. Then after it divides and it produces hundreds of thousands of these different B cells, it's going to differentiate. So after activation, I'll kind of draw an arrow like this. You're going to have proliferation. That's where the T cell divides. I'll kind of draw the arrows in a thicker black. And then after proliferation, it produces hundreds of thousands of these different B cells. That's when it's going to go through a process called differentiation. Where the B cells are going to turn into two different types of B cells. It's going to turn into plasma cells and memory B cells. Let me make sure this is in view here. And then memory B cells. Plasma cells are really important because these guys are going to release antibodies. And we haven't talked about antibodies yet. Antibodies are really important for our body's ability to fight infections. These are little tiny pieces of proteins. They're not cells, they're not alive, but they're released by these plasma cells. And these antibodies are able to really help us fight infections effectively. In fact, they are able to knock out a lot of the viral or bacterial particles that have entered our body. If we talk about antibodies, they do a couple of different things to help us fight infection. So let me kind of overview this right here. So antibodies, right? Here I'll just draw a little picture. This is a plasma B cell right here. It's going to release these little antibodies. They look like these little pieces of, I don't know, proteins that have been released. They kind of look like that. I'm trying to label this. So this is antibodies are right here. This is a plasma cell, right? Plasma B cell. And what these antibodies do is that they're going to fight infections in four major different ways. And we can summarize this with the acronym PLAN, P-L-A-N. P stands for precipitate. So what these guys are going to do is that, let's say there's like a little viral or viral particle or a little bacterial particle. Let's say there's a little bacterium right here. Oh, I should have done it in orange, but that's all right. So we'll have like a little viral or bacterial cell right there. These antibodies are going to stick to it, and they're going to cause a bunch of these bacterial cells to kind of stick together like that. And they're going to precipitate out of the body's fluids, which means they just fall out of solution. And that makes it a lot easier for our other cells like macrophages to eat them up. Okay, so that's precipitate. L stands for lyse. This is an important one. So lyse, let's draw the same kind of bacterial cell. An antibody is going to stick to this guy, and it's going to trigger a sequence of events which causes that bacterial cell to explode. So we'll just draw him kind of exploding, right? And that is going to destroy the cell. Another name for that process is called complement, like complement if you ever come across it. A glutenate also is very similar to precipitate, and so in a glutenate it causes a bunch of bacterial cells or other cells to stick together in a big clump. This is what happens with a blood mismatch reaction. If you get blood that is not a match for you, so if you have antibodies that are sensitive to the blood that you receive, let's say you have A blood and you receive B blood, you have antigens or antibodies against the B blood, it's going to cause all those B blood cells to stick together into a big clump, which is going to be deadly and fatal because it's going to cause clots throughout your body. So an example of that would like a blood mismatch reaction. You'd have all these red blood cells that are the wrong type for you. Like if you had A blood and you received B blood, the antibodies would cause them to stick together, and that would create this giant clot that would clog your vessels and cause death. It's really actually super dangerous. And then N stands for neutralize. And what neutralize means, these antibodies are going to surround a viral or bacterial cell so that it can't replicate or bind onto anything or do its job. So an N stands to neutralize. And so then we'll just draw like a bacterial cell that has been completely surrounded by antibodies, and that completely neutralizes it. So if we're talking about the course of how long this takes, let's say you get exposed to the flu, right? So you get exposed to the flu, and you have CD4 and T cells and B cells that are a match for this flu virus. Well, the first thing that happens is these CD4 T cells and the CD8 T cells are going to bind onto that viral particle, and they're going to start dividing. That takes a couple of days. The CD4 T cells finally get to a certain number, and they start releasing cytokines. The B cells are then going to be activated, but again, they have to go through a proliferation period where they start dividing. Then they have to differentiate into plasma cells. Finally, we can release antibodies. It's not until like day 4 or 5 or 6 that we start to see increased antibody levels in our bloodstream after exposure to the flu. Finally, the antibodies around day 7 reach such a high level that they're able to completely knock out the flu virus with the help of the CD8 T cells. The virus goes away, all of the plasma cells go away, all the CD4s go away, the CD8s go away, and all we're left with is memory T cells and memory B cells. Now, if we're exposed to that same flu virus, let's say a couple of weeks later, those memory Bs and memory Ts are ready to spring into action. They immediately convert back into plasma cells for B cells, and then CD4s and CD8s for memory cells. And they're able to produce a bunch of antibodies, and the CD8s kill viruses right away, and we're able to knock out that infection so quickly that we didn't even feel any symptoms. Now, here's the crazy thing about HIV, which makes it so deadly. HIV virus targets mainly CD4 T cells, and it destroys them. So the virus enters these CD4 T cells, it replicates, and when that happens, it causes these CD4 T cells to die. So over the course of several years, it takes a long time, the number of CD4 T cells just plummets. We're able to produce antibodies that are effective against HIV, and so we're able to kill billions and billions of the HIV virus, But the HIV is so good at replicating is that our immune systems can't keep up with how many viral particles are in our bodies. So over time, CD4 T cells are basically eliminated. If we don't have CD4 T cells, we can't produce cytokines. If we can't produce cytokines, we can't activate CD8 T cells, and we can't activate B cells either. That means that we've lost all of our CD8 T cells. If we can't activate B cells, we've lost our ability to produce antibodies for any illness that we may come into contact with. And that's AIDS, right? So full-blown AIDS occurs when our T cell value is down to 0. We're unable to produce antibodies, and these secondary infections, which are typically quite minor, are then able to wreak havoc on our bodies, leading to death. All right? So hopefully that helped out a lot. This is a very quick overview of the immune system, but that's it. Thank you.